always teach this talking like Sean Connery. No, I'm kidding. All right. Is STP an ICND1 or ICND2? Spanning tree is covered 100% in ICND2. Obviously, you guys didn't see any spanning tree questions on your first test, right? But it is covered heavily in ICND2. And it can be a very challenging topic because there's a lot of stuff happening in spanning tree. So we're going to talk about spanning tree in quite a bit of detail. There's basically two parts to spanning tree. You have to understand the algorithm. It's almost like a routing protocol. It's very much like OSPF with costs and paths and all that stuff. But then you also have to understand the configuration and the versions of the different versions of spanning tree. All right. So this is a very typical design in an enterprise network where you have a collapsed core, distribution switch A, distribution switch B, running routing, multi-layer switching with VLANs and SVIs. And then you have your access layer redundantly connected to the core. So if distribution A goes down, distribution B can take over and vice versa. But there's an inherent flaw in this design from a layer 2 perspective. And that is that it creates layer 2 loops. Layer 2 loops are very bad. Very, very bad. All right? If an ARP request gets created, for example, and you're not running spanning tree, essentially what's going to happen is that ARP request is going to get flooded around the network over and over and over and over and over again until the network is completely saturated with traffic. Do frames ever die? Do you guys remember any kind of time to live for an Ethernet frame? Nope. So if an Ethernet frame gets caught in a loop, it stays there forever. Because what do switches do with unbounded traffic? They flood that out of every port except for the port it came in on. So it doesn't even just have to be an ARP request. It can be any unbounded traffic is going to crash the network. And it will crash, by the way, very, very quickly. The network will go down quickly with layer 2 loops. So what do? Obviously, we know what we do. We implement spanning tree. All right? This is just a representation of what I was just talking about. A data link layer frame header does not have a time to live. It has a preamble, destination MAC, source MAC type field. That's it. If an IP packet gets caught in a loop, at least it will die eventually, because every time it goes through a router, the time to live gets decremented by 1. But at layer 2, that doesn't occur. At layer 2, that does not occur. I get people telling me all the time, we don't need a stinking spanning tree. We only have one switch in our network. We don't have that fancy redundant design. Do you need spanning tree if you only have one switch in the network? Absolutely. Have you guys ever seen anything like that? Right? Yeah. Even a loop on a local switch, can bring down that switch. Because think about it. If an ARP request gets generated by a host, it's going to go out a port, it's going to come in, it's going to go out, it's going to come in, it's going to go out, it's going to come in, and even that switch can get overwhelmed with vast amounts of layer 2 traffic. There should never, ever, ever be an instance where you don't implement spanning tree. Okay? It's turned on by default on every Cisco device, every Cisco switch, and you shouldn't turn it off. Now, Granted, the method of spanning tree that's used by default is the crappiest method that you can use, but we'll talk about that in a little bit. Overall, that's just a really nasty network for many reasons. All right? They got the power just sticking right out the wall, right across the aisle that you walk through. I mean, look at the power cables. They just come right on here and just go right into the rack. It's hilarious. Pretty poor design.
I think I worked there.
Yeah, that's probably your handiwork, right?
Yeah, I didn't let you in that closet and take the picture.
Yeah. How did you get my picture? Yeah. When we talk about, when I teach the CISSP, we talk about data center design and whatnot, and hot aisles and cold aisles and all these techniques to make sure that the data center runs efficiently. That's not one of them. All right? So we still want to have the ability to have the redundancy, the physical redundancy, but we don't want to have those redundant paths. It's kind of a conundrum. So of course the solution is STP, the spanning tree protocol. All right? Now, there are only about 10 versions of spanning tree. 802.1d, 802.1w, 802.1s, PVST, PVST+, PVRST+, MST. There are lots and lots of different versions of spanning tree. And believe it or not, we're going to talk about pretty much all of them. We're going to focus our attention primarily on PVRST+, but, or 802.1s if you want to call it that. So, forgot to tell you, spanning tree allows us to have the physical redundant paths, but the goal of spanning tree is to eliminate those redundant paths logically. To shut down certain interfaces on the network so that those redundant paths don't exist. But what happens if something fails? What is spanning tree supposed to do? If something fails, spanning tree is supposed to be able to recover and fail over to another link, right? We're going to look at that algorithm and how that happens. The way that switches exchange information is through the use of something called a BPDU. Bridge Protocol Data Unit. By the time we're done with this chapter, you're going to be able to look at, this is a Wireshark capture of a BPDU. By the time we're done with this chapter, you're going to be able to look at this whole thing, and you're going to know what every single one of these numbers mean. You're going to know what the 24576 means. You're going to know what the 10 means. You're going to know what the max age means, what the hello time means, what the forwarding delay means. You're going to know what the designated port role means, what learning means, what forwarding means. All of this stuff. It's great. Everything you need to know about spanning tree is in this picture right here. We'll come back to it. As I start to kind of peel back the onion, I'm going to come back to this and say, okay, now do you understand what these numbers are? Do you understand what the bridge ID is? Do you understand what the root ID is? Do you understand what the flags represent? Of course, you're going to say yes and shake your head because it's exciting. All right? So the first thing you need to know about spanning tree is this concept of a bridge ID. In spanning tree, switches identify themselves to other switches through BPDUs, but the primary way that we decide how the spanning tree topology looks is through something called the bridge ID. Traditionally, the top one you see there, traditionally the bridge ID was two values. It was priority and MAC address. Okay? The bridge ID is the most important concept in spanning tree. because every decision that we make in spanning tree is based on bridge ID. Priority is a value that you can set as a system administrator. Every single switch, not only Cisco, but everybody else, uses a default priority of 32,768. MAC address is the base MAC address of the switch. Does anybody happen to know what command we run on a Cisco switch to see what the base MAC address is? Show version. Is that what you said? Yeah. No, I heard you. I thought that's what you said. I thought you said, shut up, asshole. No. Show version, right? At the very bottom of show version, I don't think show inventory will show you that. Show inventory will show you serial numbers and stuff, but it won't show you MAC addresses. Okay? Show version. At the end of show version, there's actually a field, base MAC, and you'll see the base MAC. That is the MAC address that's used in the bridge ID. So it doesn't matter what VLAN it is, it's the same bridge ID, or the same MAC address anyway. Cisco didn't really, and well, actually, no, they didn't invent spanning tree, because there was a version of spanning tree called CST before Cisco did their PVST. But Cisco said, you know what, we want to be able to optimize spanning tree per VLAN. So what we're going to do is we're going to change the bridge ID, and we're going to create this thing called an extended system ID, or extended bridge ID with a system ID. They took the priority field, which was 2 bytes, and they split it into 2 pieces. The top 4 bytes were still used for priority, top 4 bits used for priority, and then the bottom 12 bits were used for the extended system ID. What happens to also be 12 bits when it comes to switches? What field is represented by 12 bits at layer 2? The VLAN ID field. So there's a reason why that extended system ID is 12 bits, because guess what goes into that field? The VLAN ID, which gives us the ability to run spanning tree per VLAN. Cisco runs spanning tree per VLAN. We'll talk about why that's important later on. There is an instance of spanning tree called CST, which stands for Common Spanning Tree. That's going to use the top bridge ID format. Cisco uses the bottom bridge ID format. And actually, most vendors use the bottom bridge ID format. What would be the benefit of being able to, what is the benefit of being able to identify a spanning tree instance per VLAN? Any ideas? Localize to load share. To be able to go, okay, I want distribution switch A to handle all the traffic for these VLANs, and I want distribution switch B to handle all traffic for these VLANs. Well, we'll say those VLANs. All right? I think I have a diagram that kind of depicts that concept. We'll see that maybe a little bit later on. So by using, or by splitting that 2-byte field into 2 pieces, the purple piece that you see on the screen here, that's the VLAN ID, goes from 1 to 2048. And then, rather than start the bits over at 0, they kept the same weight for each of those higher order bits. So what is the lowest bridge priority I can set? Based on what you see on the diagram there, what is the lowest bridge priority I can set? Before you answer, think about what I'm asking, because everybody always gets this wrong. What is the lowest bridge priority I can set? Anybody?
49.6.
That's what everybody always answers. Damn it.
0.
0. 0 is always the lowest, right? Turn all the bits off and it's 0. The next is 4,096. Right? Because the green field represents the priority field. Not 4,097, 4,096. Okay, we're talking specifically about the priority. I'm not talking about the extended system ID when we're combining the VLAN. So my first priority value is 0. My second priority value is 4,096. My third priority value is 8192. My fourth priority value is 12,384, something like that. You get the idea. Or not, whatever, you get the idea. All right? How many possible priority values do I have then? If it's a 4-bit field, how many possible values do I have? Binary math, guys. This is where learning subnetting comes into play. 2 to the power of 4? 16. Right. 16 different priority values. The maximum value I can have is 65,000. What? Is it 65,536 or 535? It's definitely not 65,535. All right? Because the max you can have is 1, 2, 3, 4, 32,768 plus 16,384 plus 8192 plus 4,096. These bits on the right, the purple bits, those are reserved for identifying the VLAN. Lloyd, is this the first time you've seen spanning tree or the first time you've seen a reference to extended system ID? I'm going to go ahead and assume the first. All right. Oh, the extended system ID. Yeah. That's surprising because that's what Cisco uses. You know, this is kind of one of those topics. It's like EIGRP and OSPF where you can learn the basics and kind of get by, but I don't like to deal in just the basics when it comes to these important protocols. Because we can run spanning tree per VLAN, I can make one switch the root for one VLAN, and I can make another switch the root for another VLAN, which allows me the ability to load share the traffic up to the distribution layer. Imagine on this diagram that the top two switches are my distribution layer, and the bottom switch is the access layer. Okay? Does that mean if the left switch fails, VLAN 1 is SOL? No, because what happens when the left switch fails? That switch takes over for VLAN 1. So the switch on the right is a backup for VLAN 1. The switch on the left is a backup for VLAN 2. Spanning tree does not provide the ability to do dynamic load balancing. And I'm very particular about the way that I mention this. You'll hear me use the term load sharing quite a bit. Technically speaking, load balancing is a dynamic process. Load sharing is a manual process. That's the way Cisco usually refers to it. Like, for example, HSRP, the Hot Standby Routing Protocol. It is what we call a first hop redundancy protocol. It is a load sharing protocol. It's not a load balancing protocol. Load sharing means you can manually force traffic to go certain ways, but it doesn't dynamically do it. It does it based on calculations. A routing protocol does load balancing, unless it's BGP. BGP doesn't do load balancing, it does load sharing. All right, I digress. All right. You could see the benefit for this, right? If I was using what we call common spanning tree, CST, common spanning tree, which by the way, 802 versions of spanning tree, 802.1W, 802.1S, 802.1D, they all use common spanning tree. Common spanning tree is a term we use to describe that every VLAN has to follow the same topology. Cisco doesn't run common spanning tree. Cisco runs per VLAN spanning tree, which allows us to optimize spanning tree per VLAN. Test question, test answer. Ding, ding, ding. All right. Here are some of the different versions of spanning tree. The spanning tree protocol. 802.1D. D stands for don't use this version of spanning tree. All right? This is what we call a common spanning tree protocol because every VLAN assumes the same topology, meaning that you cannot assign a route per VLAN. Every VLAN just assumes the same route. Also notice the convergence time is extremely slow. We saw that in Packet Tracer. The default mode of spanning tree in Packet Tracer is 802.1D. And every time you plug something in, this little orange dot shows up, and about 50 seconds later, it goes away. That's how quickly common spanning or 802.1D converges. PVST plus. PVST stands for per VLAN spanning tree. Okay, the plus, there was actually one without a plus. The plus is all the enhancements that Cisco added to spanning tree. Port fast, BPDU guard, loop guard, root guard, ether channel guard. There's a whole bunch of enhancements that Cisco added to spanning tree. We don't get into all those little tiny enhancements in this class. We tend to talk about those in the CCNP class, but the key that I want you to get from this is that we're running spanning tree per VLAN. So if you have 20 VLANs in your network, you're going to have 20 instances of spanning tree. That's why it says that the resource needed are high, because we're duplicating spanning tree instances more than once. Now, why does it say that convergence is slow? Well, essentially, PVST plus is 802.1D. It uses the same deterministic timers as 802.1D. The only difference between 802.1D and PVST is the ability to run spanning tree per VLAN. Rapid spanning tree. Rapid spanning tree. 802.1W. Shouldn't forget that W because it's rapid, right? Elmer Fudd? Yeah. RSTP, Rapid Spanning Tree Protocol. Now, it's pretty much exactly the same as 802.1D. The only difference is it's much faster. The timers that we use in 802.1W are significantly faster. It might take 802.1D about 30 to 50 seconds to converge. In 802.1W, we're converging in about 3 seconds. So it is significantly faster. Wolverine heals fast, yes. Absolutely. And D is we don't use this version, right? Okay. Now Cisco, of course, has their own version of rapid spanning tree called rapid per VLAN spanning tree. And then we have the spanning tree that we always use in most enterprise networks. It's called multi-instance spanning tree or multiple spanning tree. We don't talk about MSTP in this class. We talk about MSTP in the CCNP class. Really, that's the type of spanning tree you should be running in most enterprises. But I'll tell you, the most common form of spanning tree that we see is RPVST plus. All right? You guys are not going to be tested on all the unique versions of spanning tree. The one thing I want you to take away, though, is that all of these versions of spanning tree are compatible with each other because they all use the same fundamental algorithm, STA, the spanning tree algorithm. So if there's any reference on the exam to whether or not spanning tree is compatible, just select that it is because all versions of spanning tree are compatible. Now there are some restrictions, like for example, multiple spanning tree cannot be combined with other versions of spanning tree, but it does use the same overall election process, which we're going to learn. What is the goal of spanning tree? You turn on your network. What is spanning tree trying to accomplish? In general, not specifically, but in general. To get rid of the loops, right? That's the ultimate goal of spanning tree. Spanning tree is not there to decide how traffic is supposed to flow through the network. How traffic flows through a spanning tree network is a side effect of the spanning tree process. All right? So the goal of spanning tree is to figure out what links to turn on or leave on and what links to turn off so that the loops get removed. But of course, we want to do that in the most efficient way possible. We don't want to turn off the links that are better than other links. So there's a whole election process that takes place. Okay? There's a whole election process that takes place that allows us to determine what the spanning tree topology is going to look like. I was just seeing what was coming up. These are details of what we just saw on the table. I'm not going to go through all these. You can see, I put this in here just to give you guys an idea of how spanning tree progressed. Hey, there's those guys again. Digital Equipment Corporation. What did those guys invent besides spanning tree? Ethernet. Right. Well, they got help with Xerox, but those are the same guys that were in bed with Xerox to invent Ethernet. They invented bridging. All right? But, you know, they didn't grow with the times and they went away. I guess they figured.
I thought they turned into Cisco.
They did not turn into Cisco. They may have been acquired by Cisco. I don't know if that's true or not, but probably the people that work there move over to Cisco. Yeah. I mean, that seems kind of like a natural progression. All right? So here's the general process. We're going to go through this in detail later on as we move through the chapter, but here's the general process of how we move through different spanning tree states. There are two things that you guys are going to have to know for the test with regard to spanning tree. You're going to have to know what a spanning tree state is, and you're going to have to know what a spanning tree role is. There's a distinct difference between those two things. The spanning tree state is what you see on the board here. Is spanning tree disabled? Is the spanning tree port forwarding? Is the spanning tree port blocking? Is the spanning tree port listening or learning? Now, of all these 5 states that you see up on the board, which of these states are the result of a converged process? What states result after spanning tree has done its thing? Forwarding and blocking. That's exactly right. Forwarding and blocking. So when spanning tree is converged, meaning that it's gone through its entire election process, it's figured out what the topology is supposed to look like, the stable states are blocking and forwarding. Some ports are going to get blocked, some ports are going to forward. Listening and learning are what we call transitionary states. The switch is going through these processes to try to figure out what ports should be what. The listening and learning states are 15 seconds each. 15 seconds to go through the listening and learning state. All right? Now we're going to learn the difference between listening and learning and find out what applies to what version of spanning tree, but not right now. We need to talk about the algorithm first. Another thing that you're going to have to know for the test is port roles. Now, a couple things I want to point out on this particular slide because you will have to know this for the exam. A blocking port, well, that's pretty simple. What is a blocking port? It is a port that's not forwarding client's traffic. It's still sending and receiving BPDUs, but spanning tree has determined that that particular port, if it were active, would cause a loop. So it's going to turn off that port. The ports are not actually physically disabled. They actually will still have a link. They're just not forwarding traffic. Listening is a process where the switch is trying to determine what the port's state should be, but we're still not forwarding traffic in the listening state. STP, by the way, not RSTP. Notice that in spanning tree, we have listening. What did they get rid of in rapid spanning tree? They got rid of listening. Rapid spanning tree does not have the listening mode. It has learning, but not listening. Also, blocking was renamed to discarding. Test question, yes. It's still the same thing as blocking. Discarding is blocking. So I don't know if it's really a new port state, but nonetheless, it's there. Learning mode. Learning mode is the same as listening mode. The only difference is I'm still blocking client frames, but I'm also mapping their MAC addresses in the database. In listening mode, we're not even building our database. In learning mode, we're still blocking clients' frames, but we're updating our MAC address table so that if we do have to start forwarding frames, we have a way of doing that. So both the listening and learning states, traffic is not being forwarded. There's only one state where traffic gets forwarded, and that is the forwarding state. So with rapid spanning tree, when rapid spanning tree is fully converged, every interface is in one of two states, discarding or forwarding. So far, so good? A lot of terms with spanning tree, right? The theory of spanning tree is a lot more difficult than the configuration of spanning tree. Spanning tree configuration is pretty simple. Then we have this thing called port roles. Now, I'm not going to go through the details of what each of these port roles here are on this slide, but I do want you guys to understand the distinct difference between a port role and a port state. A port role is a function of an interface. A port state is the mode of an interface. So forwarding and discarding is a mode. Alternate, backup, those are functions. Okay? Root ports are forwarding, designated ports are forwarding, everything else is discarding. Alternate backup are discarding, disabled, I don't even know why they define that as a port role, because disabled means the port's turned off, but I didn't put that on there, that's something Cisco did. All right, the port's disabled. Reminds me, Olympics start today, right? It's better than winning a gold medal in the Special Olympics. Not being in the Special Olympics. All right.
No off-color joke there.
I have a midget joke too, but unfortunately we have mixed company, so I can't tell that midget joke. So the next step for us is to learn the terminology. Learn what a root port is. Learn what a root bridge is. Learn what designated ports are. Learn what non-designated ports are. All of this is related to something called the spanning tree algorithm. Now the thing about the spanning tree algorithm that's extremely important, and I found this out many years ago after banging my head against the wall trying to get students to figure out how spanning tree works, is you cannot read about spanning tree and figure out how it works. You have to see it in a visual format. You have to see it applied to a diagram. Because I can tell you what a root bridge is, I can tell you what a root port is, and it makes perfect sense to me because I'm visualizing it. So I'm going to come back to this slide. You know, I forgot to, I kept saying I was going to go back to this. One more. One more. Remember this? Let's break down some of these numbers. The root, we don't quite know what that is yet. We're doing that next. The root is the anchor point in the spanning tree topology from which all other spanning tree elections are made. Now we know what the 24576 is. 24576 is the priority. What is 10? Remember, that's an extended system ID. What is 10?
VLAN.
The VLAN. And then we have the MAC address. So we know that this is a BPDU for VLAN 10. Right? Okay? Port role is designated. We don't know what that is yet. We're going to learn that. Learning. The learning flag is on. Is this switch converged? No. Because the only time you're ever in a learning state is if you're doing convergence, if you're performing convergence. Okay? What version of spanning tree is this BPDU for? RSTP, Rapid Spanning Tree Protocol. All right? So we're starting to see some of these values. Hello timer. I didn't talk about that, but that's how often BPDUs are sent out. Believe it or not, for every interface on a switch that's running spanning tree, BPDUs are sent out every 2 seconds. These are relatively benign frames. They're multicast frames, relatively small. So the fact that they go out every 2 seconds on every interface per VLAN, not a big deal. Forwarding delay is 15 seconds. That's how long I stay in the listening and learning state. Although we won't have a listening state here. How do I know I'm not going to have a listening state with this BPDU? Because it's rapid spanning tree. Rapid spanning tree doesn't have a listening state. It only has a learning state. So as I promised you guys, you're going to be able to look at a BPDU capture and understand what that means. We got to fill in a couple more gaps here though. This is the topology that we're going to use to hammer home your understanding of spanning tree. Okay? Now on the test, you're going to have similar diagrams, although not as complex, where you're going to have to figure out the spanning tree topology on the exam. There's 37 steps to figure out the topology. All right? So we're going to go through all 37. It takes about 15 minutes per step. No, I'm kidding. There's only 4 steps.
That's cool, man. That's cool.
There's only 4 steps to spanning tree. And actually, the first and last step are so simple, it's almost 2 steps. Okay? Step number 1. Pick the root bridge. Now we're going to see this term bridge a lot, right? Because when was spanning tree invented? When bridging was happening and not switching. What is the difference between a bridge and a switch? Most of you guys probably never even worked with a bridge before. But before switching we had a bunch of hubs in the network. We would put bridges in our networks to make them more efficient. A bridge is basically a switch with fewer ports, like maybe 2 or 4 ports, and it did everything in software instead of hardware. But it was a device that could learn MAC addresses and do forwarding and filtering decisions, just like a switch does. So the term bridge and switch are kind of interchangeable. All right? But because spanning tree was around before switches were popular, it was around for bridging. That's why we see the term bridge a lot. So the very first step in spanning tree is to pick your root bridge. You have to pick your root bridge. The root bridge is the anchor point from which every other spanning tree decision is made. So if you don't choose the root bridge correctly, your entire spanning tree calculation is going to be incorrect. How do we choose the root bridge? This is done per VLAN. All of this is based on per VLAN spanning tree. The root bridge is chosen based on the lowest bridge ID. This is one of the first times where the lowest matters, not the highest. Of course, there's 2 ways to write a bridge ID. You can have one that's just priority and MAC address, or you can have one that's priority, VLAN, and MAC address. But in either case, whichever one is lower wins. Priority takes precedence, and the default priority for all Cisco switches is 32.768. Okay? So when does MAC address come into play? If there's a tie with priority, we use MAC address to break the tie because MAC addresses are globally unique. Based on what I just told you, which switch in this topology is going to be the root? Which switch in this topology is going to be the root? The red numbers. The red numbers are priority. The green numbers are MAC address.
Lowest priority and lowest MAC.
Switch D? You guys sure about that? Switch C and switch D have a tie. They both have, clearly they have the lowest priority, right? 4096. How do we compare MAC addresses? What's lower, $1,000 or $1,010? 1,000, right? You compare from left to right. 0, 0, 0, 1. What's lower, 0 or 1? Not a trick question. All right? So switch C is my root because it has a lower MAC address than switch D. Got me?
So you just look at like the octets individually, they're the same back.
Just look at each hexadecimal letter or number from left to right. You don't have to look at the whole number. You just compare digit by digit.
And letters are higher than numbers.
Right. Letters are higher than numbers because it's hex. So that's step number 1. That's not too bad, right? But wait, there's more. We got to go to step 2. Okay? Before we move on to step 2, does everybody understand how switch C became the root? Okay? Because clearly that's the most important part of the algorithm. If you choose the wrong root, every other calculation that you're doing is going to be wrong. Because all spanning tree calculations are based on who becomes the root. Now, step 2 is the most complicated step. Step 3 is less complicated. Step 4 is not complicated at all. But step 2 really can be the most difficult step to grasp. Because in step 2, we are electing our root ports. These are actually called root ports. A root port is defined as a port on a switch that provides me the best path to the root. And these paths are based on cost. There's a table here. You can see the different spanning tree cost values. This is an IEEE specification. Cisco follows this. So this is not just Cisco specific. Everybody pretty much follows the same specification. If a link to the root is 100 meg, it's going to cost me 19. If a link to the root is a gig, that's only going to cost me 4. And just like with routing protocols, the lower the cost, the more preferred the path. Okay? These are cumulative costs. Cumulative. So if I look at my diagram here, every one of these links is fast Ethernet. So what is the cost of each of these links in this topology? No. 19. So each one of these links costs me 19. Okay? Now on the test, they're going to try to trick you. On the exam, they're going to try to trick you because they're going to have a gig interface on one side of the link. They're going to have a fast Ethernet interface on the other side of the link. What is the cost of that interface? What is the cost of that link? If it's gig on one side and it's fast Ethernet on the other side, what is the speed? Fast Ethernet. All right? Don't let them fool you. It's going to have a cost of 19. Because even though an interface is gig, if the other side is fast Ethernet, the fastest speed I'm going to get across that link is fast Ethernet.
So when does it become cumulative?
It's cumulative in the sense that we add up the path cost. Right? Depending on where we're at in the topology. It's not just one link, it's all the links to get to the root. Don't worry, we're going to go through this. All right? Now this is where it gets a little bit confused. All right? With regard to the root ports, we do this on every switch that is not the root bridge. There is only one root port per switch, no exception, per VLAN. We have how many switches in our topology?
4.
4, right? How many are not the root? 3. How many root ports are we going to have in our topology? 3. 1 root port per switch, per VLAN. We're assuming we're only running 1 VLAN in this case. The root port is the port to the path that has the least total path cost to the root. What? Yeah, I know. It doesn't sound very good. Okay? Let me give you one example. Let's look at switch D. Switch D is an easy one to deal with, right? How many directions can switch D go to get to the root? Well, 3. It can go over port 9, it can go over port 7, or it can go over port 1. If it goes through port 1, what is the cost for that path? 19. If it goes through port 9, what is the cost for that path? 19 plus 19 plus 19. See what I'm saying? That's where the cumulative part comes in. It's cumulative path cost. It's like OSPF. So clearly, which port is going to become the root port for switch D? 0, 1. Right? Now what about switch A? Am I going to go to the right or am I going to go down? I'm going to go to the right. But here's an issue. Port 1 has a cost of 19. Port 8 has a cost of 19. And I can only choose one of those ports as my root port. How do we handle that? Well, let's go to our handy dandy slide here. What if I have 2 paths to the root bridge through the same neighbor and they have the same path cost? What do? I choose the port with the lowest interface number. So in the case of switch A, port 1 becomes the root port. So far, so good?
Pick the lowest interface then if it's got multiple paths to the same switch with the same cost, the same bridge with the same cost.
You mean like B? Or,
Well, like switch A,
yeah,
it's got 0, 1 and 0, 8.
yes. In the same direction, we always pick the lowest port number. We pick the direction first, and then if there's a tie in the same direction, we always pick the lowest port number. But what about switch B? Now we really have a conundrum. Because I can go through switch A, it's got a cost of 38, 19 plus 19. Or I can go to switch D, and it has a cost of 38, 19 plus 19. So now I've got a tie. I can go one way or I can go the other way.
So it is still the lowest port.
It is not the lowest port. The tiebreaker here is I'm going to go to the neighboring switch with the lowest bridge ID. So I choose to go towards switch D because D has a lower bridge ID than A. Now the reason they do that is because if switch C fails, switch D is more likely to become the root than switch A. And if I'm already going that way, it's better. Now, I've picked a general direction. But I still have a tie, don't I? I have to choose between port 5 and port 7. Now I choose the lowest port number. I told you the second step was the most complicated. All right, but we get to see a pretty little picture of that process completed. Now, just sit back, take it in, look at the diagram, think about the process we went through to first get the root bridge. Think about the process that we went through to get those green boxes. Kind of melt it into your brain there for a little bit before we move on to the next step. We picked the root bridge based on lowest bridge ID. Check. We picked the root ports based on the least path cost to the root. If there's a tie going to the same neighbor, we choose the lowest port number. If there's a tie going to different neighbors, we pick the neighbor with the lowest bridge ID. Okay? So those green boxes have now assumed not only a port role, but they've also assumed a port state. What port role have those ports assumed? That's a state, which is why I asked that question. They're in a forwarding state. What is their port role? They are root ports. That is their port role. Their state is forwarding. Their role is a root. Got it? How you guys doing online there? You guys doing okay? You following along? Anybody put me on mute yet? We're over the top of the mountain now. Now we just have to go downhill. All right? Which brings us to step number 3. Only 34 steps left to go. Okay? Step number 3. Designated ports. Is a designated port a state or a role? It is a role. The state of designated ports is a forwarding state. On every single switch segment, a segment is defined as the links between the switches. How many segments do we have in this topology? 7. Okay? Just keep that number in your head. On every segment, we select one designated port. So when we're done, we're going to have 7 designated ports. A root port can never be a designated port. So if a segment already has a root port, then the other side of that segment is automatically designated. Which one of these are designated? Port 9 on switch C, right? Port 5 on switch C. Port 9 on switch D. Follow me? If one side is root, the other side has to be designated. There's no exception to that rule, ever. So you don't even have to really do a calculation there. Since FA01 on switch A is a root, FA09 on switch C must be designated. Okay? If there is no designation on the link, then the port that is connected to the switch with the lowest bridge ID becomes the designated port. What? I know. I get it. Confusing. The links between switch B and switch A. Are there any designations on the links between switch B and switch A? Not presently, right? Which side becomes designated? The side that is connected to the switch with the lowest bridge ID. So on the links between switch B and switch A, which sides are designated? Switch B. Why switch B? Lower MAC address. D is lower than F. You guys follow what I'm saying? What about between switch B and switch D? We already know port 9 is going to be a designated port because the other side is a root. But what about the bottom link between switch B and D? Which side is going to be designated? The bottom link between switch B and D, which side is designated? Port 7. Switch D. The bridge ID of switch D is lower than the bridge ID of switch B. Follow me? Let's look at it in a pretty picture so that you guys can see everything converged. Why did port 9 and 7 on switch D become designated? Because the bridge ID on switch D is lower than the bridge ID on switch B. Is the root ever going to lose that? No, the root is never going to lose. So every port on the root is always designated. Every port on my root switch is always designated. Okay? Again, we're going to take pause here for a second. Kick back and look at the diagram and say, okay, why did that happen? Why did that happen? Any questions?
You start over?
Sure.
Just kidding.
I'll start over in about 3 weeks when I teach this class over again. I taught this class, one time I taught this class 3 weeks in a row. Three different groups of people. I was getting so mad at the people in the third group because I'm like, come on guys, I already told you this stuff. And they're like, no you haven't. Yeah. And I hadn't. I had told the people before them, obviously.
Wow.
It was brutal, man. Teaching that class 3 weeks in a row. That was brutal. The best I can do now is maybe once a month. But, okay. What do you suppose the last step is? By the way, what is the port role of those yellow ports? Designated, right? What is the port state? What is the port state of a designated port? The port state is forwarding. Forwarding state. All right. What do you think the last step is? The last step's the easiest one.
Gotta kill some ports.
Whatever's left is blocking. There's no calculation here. Whatever's left is blocking. Did we get rid of our loop?
Oh,
Sure enough, we did. See, when you get used to spanning tree, when you get the 4 steps down, it's really, really simple. Let me show you. I used to make the students do this, but not so much anymore. I just kind of do it as a, it's kind of like learning subnetting. After a while, you get good enough at it that it gets pretty easy. Let's do STA example hard. So here's my topology. Now what's amazing is that this process works no matter how complex the topology is. Let me move these guys over here. This guy becomes my root. That's my root. This is a root port. 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 Whoa! How did you do that so quickly? Well, this is a cost of 19. This is a cost of, these are gig links, so that's a cost of 8. So I know I'm going to go that way, and I choose the lowest port number. This is a cost of 19. This is a cost of 4 plus 19. This is only a cost of 4, so I'm going to go that way. This is a cost of 4 plus 4. This is a cost of 4 plus 19. This is a cost of 4 plus 4. So I can go this way. Dang it. I can go this way, or this way. If I can go this way or this way, which way do I choose? I choose based on the lowest bridge ID, which is that way. Okay? Here, cost of 4 plus 4 plus 4. Oops, I did that one wrong, actually. I'm sorry. My bad. That's a root port. This is going to be a designated port eventually anyway. Actually, that's going to be a blocking port. Dang it. I want to put a black dot on that one. I'm being all fancy trying to do it quickly here. All right. Cost of 19, cost of 4 plus 4 plus 4 is less than 19. So I know I'm going to go this way. I choose the lowest port number. So those are my root ports. My designated ports. Well, I know that's designated because the other side is root. I know that's designated. I know that's designated. I know that's designated. I know that's designated. The bridge ID here is lower than the bridge ID here, so that's designated, and that's designated. The bridge ID here is higher than the bridge ID here, right? So that's designated. The bridge ID here is higher than the bridge ID here, so that's designated, and the bridge ID here is lower than the bridge ID here, so that's designated. Of course, the root never loses, so all those ports are designated. Oops, this one here, 16384, 4096, that's designated. Does every segment have a designated port? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the only thing remaining is my blocking ports. That's a blocking port, so that's a blocking port, so this line goes away. These are blocking ports, so these lines go away. This is a blocking port because everything left over is a blocking port. This is a blocking port. Not that top one, but the bottom one. So that line goes away. That's a blocking port, so that line goes away. These two are blocking ports, so these lines go away. All right. I guess that's about it, isn't it? Did we get rid of all of our loops? Yep, because how is my traffic flowing? Here to here. Make that bigger. Here to here. Here to here. Here to here. Here to here. And here to here. Okay. So the point is, it doesn't matter how complex the topology is. If you follow the 4 steps, you'll get rid of the loops. Every time. Okay? Let's see what we got left here. We pretty much got the configuration left. So let's go through these last few slides here, and then we'll take a break. You cannot change the MAC address of a switch, so the only way that you can influence who becomes the root is by modifying the priorities. You do that in global configuration mode. First of all, the default mode of spanning tree on a Cisco device is PBST, which is a variation of 802.1d, which we don't want to use, right? So to switch to PVST plus or rapid spanning tree, we use the command spanning tree mode rapid. That will change us from PVST to RPVST, rapid spanning tree. What do you think the command spanning tree VLAN 10 root primary does? It makes that switch the root for VLAN 10. It's actually what we call a macro. So what the end result of executing that command is a priority gets set. What the switch does is it looks at all the BPDUs it gets from everybody else, and it sets the priority on that switch lower than everybody else. There is a limit to that though, isn't there? Because what's the lowest I can go? 0. So if somebody is already at 4096, the only thing I can do is go to 0. If somebody else is at 0, then we have to rely on MAC address. Okay? What do you think the command spanning tree VLAN 20 root secondary does? It sets the priority for that switch to the second best value. So effectively, on this switch here, I'm making this switch the root for VLAN 10, and I'm making it the backup root for VLAN 20. Does that make sense? What would I do on the other switch? I would make it root primary for VLAN 20 and root secondary for VLAN 10. See, it's so simple to configure. You don't even have to calculate priorities. You let the switch figure out what priorities should be used. Now, you can calculate them if you want. That third option, you would not normally do that if you're doing the first two. I just put it on there so that you can see you can actually set the priority manually instead of allowing the switch to decide what the priority should be. I generally will use the first two options in most cases. But that doesn't prevent somebody else from coming along later on and setting their value lower. That can still happen. All right? How do I verify spanning tree? Well, there's really only one command we use. This one I put in here, it's not really used that much, but the one command that we use to verify spanning tree, show spanning tree. This is the one that you're going to see on the test. What mode of spanning tree am I running?
RSTP.
Rapid spanning tree protocol. Why did this switch not become the root for VLAN 1?
Max higher.
The MAC is higher, but we didn't use the MAC in this case. The priority is higher. The priority of my switch is 32.768. The priority of the root is 24.576. Remember, the VLAN is added on top of the priority. Remember, the VLAN is part of the number. So the priority is, if this were VLAN 10, this would say 32.778 because we're adding VLAN 10 on top of the configured priority. In this case, this is spanning tree for VLAN 1. Now let me ask you guys, does a switch have to be the root for every VLAN? No. So just because a switch is not the root for one VLAN doesn't mean it cannot be the root for another VLAN, because Cisco runs spanning tree per VLAN. All right? You see the port roles and the port states. This is actually a switch in a transitionary state, because I see listening, which is actually very strange. I got this from Packet Tracer. That should not happen, should it? No, I should not see listening in rapid. There is no listening state in rapid. There's learning state. So that's another Packet Tracer bug. I'm going to have to get a new capture from that. That should be LRN, learn. There is no listening state in rapid spanning tree. Only learning, discarding, or forwarding. Okay? So one of two things is wrong in packet tracer. Either it's misinterpreting the spanning tree type, because if this was regular spanning tree, that would be valid. Now there's another feature that you're tested on. There are a lot of features that we haven't talked about with spanning tree. The goal of CCNA is to give you exposure to the algorithm and maybe some of the features. Features like port, loop guard and root guard and you know, adjusting priority. Because we focus most of our attention on the algorithm. What about port fast? You guys have probably seen port fast configured before, right? Does anybody know what port fast does?
For a link aggregation.
No, it is not for link aggregation. That's port channel.
It allows
A port channel interface allows us to create a virtual interface for ether channel. Port fast allows the spanning tree port to bypass all of the spanning tree states and go into a forwarding state immediately. What kind of ports would I implement port fast on? You could do it on a trunk port too.
I thought BPDU shuts it down.
BPDU turns off the port fast feature.
I see.
Okay? But what kind of interfaces that are trunks do not receive BPDUs? What kind of interfaces that are trunks would not receive a BPDU? A router on a stick? A VMware server? So you can run port fast on a trunk. You would never run port fast going to another switch, because then you have a high potential of a loop being created. All right? But you can run port fast on a trunk. Two ways to implement port fast. You can do it on the interface using spanning tree port fast, or you can do it globally using port fast default. If you do implement it globally, it's automatically not implemented on trunk ports. So the switch is trying to protect you a little bit there. Okay? If you want to implement, it's not in the slide here, but it is a very good command to know. If you want to implement port fast on a trunk, for example, you have a trunk link that goes to a router, or you have a trunk link that goes to a VMware server, you go to the interface and you type spanning tree port fast trunk. Use the trunk keyword at the end. All right? I need to add that to this slide deck because that's kind of important. Enabling port fast on a port enables the port to come up immediately, but it does not disable spanning tree. I want to make that very clear. If a port fast port receives a BPDU, in other words, you plug in a switch or whatever, that port is going to revert back to a normal spanning tree port. And the port fast feature is going to be disabled automatically. Okay? There is one other mechanism that you guys are tested on. It's called BPDU guard. I don't know. We don't usually run this, but I guess you could. Any port that is configured with BPDU guard that receives a BPDU shuts down. So this is a way of protecting yourself from people plugging rogue devices into your network and trying to, in the security class, we'll talk about other protection mechanisms for, we'll talk about BPDU guard again. But essentially, if you have BPDU guard enabled on an interface, if that interface receives a BPDU, it goes into an error disable state. Okay? Only put this slide in here for one reason, and that's because it's on the test. Otherwise, we talk about the spanning tree toolkit in other classes. And that, my friends, as they say, is that.